All right, so it's now 9 o'clock Eastern Standard Time here in the US. So let us start. So good morning, good afternoon, good evening, wherever you are in the world. Welcome to today's webinar. And by the looks of things, this subject is obviously of great interest through the number of people that have registered to attend this session. So we're going to talk about shared components and common cores and why this can be a problem for us. But first, those of you that are new to Exida, let me tell you a little bit about Exida. We've been around for 21 years now this year, and the company was originally started by two founding members, primarily to try and help guide manufacturers to understand the requirements of what was back then a new standard called IEC 61508 for providing certified devices to meet the requirements for safety applications. And since then, the company has grown exponentially. We don't just do product certification for safety now, we also do product certification for cybersecurity to the 62443 standard. And we also do personnel certification. Some of you are CFSEs or CFSPs and been through that certification program. And I'm hoping that many more of you will do that. Coupled with that, we also now provide the full lifecycle service support for what we like to think of as the three main aspects that make up overall process safety, which from our point of view is the alarm management, cybersecurity, and functional safety. These all are very closely interrelated when it comes to process safety. And of course, they all have the same three life cycles. They all have a first phase, which is analysis, to look at what is the requirement, whether it's safety, looking at hazards and layers of protection to prevent the consequences. If it's cyber, it's looking at the threats and the countermeasures that you can put in place. And of course, if it's alarms, it's looking at making sure only the appropriate alarms are displayed to the operators in the correct priority. So those three phases are supported with lifecycle services. And on top of that, we also have a suite of tools to help us provide support for those life cycles. We are also global. We are adding offices regularly. We've just added an office towards the end of last year in Northern Ireland. Not Northern Ireland, I'm sorry. They won't forgive me for that. In Ireland, in west of Ireland, actually in Shannon. So Shannon is on the west coast of Ireland. So that's the new one that we've just added. And we're continually looking at building on the number of offices we have around the world to support our clients as close to them as possible. A little bit about me. My name's Dr. Steve Gandy. I've been in industry now more years than I care to remember. And I have a background in safety system design. I used to work in the UK for a company called ICS, designing ESD, emergency shutdown, fire and gas, and addressable fire detection systems. Since then, I moved into the automation world and then came back into safety when I joined Exida about 9 years ago. So how do we measure our success? Well, we've moved away from being just owned by two founding members. We're mostly employee owned. We also are now the leading certification agency in the world. And a lot of people don't know that. And it was a surprise to us as well when we found out. We also have over 100 global experts, and we've done over 1,000 certification assessment projects and modeled well over 500,000 SIFs with our Excellencia tool. And some of you are probably using the tool yourselves. Reference materials. We do provide a lot of books. Last year, we provided the Functional Safety for Managers book, what managers need to know. And that was primarily because of a lot of the conversations we were having with management teams. It was clear that a lot of people that come on the training courses are not managers. And so therefore managers have a responsibility and need to know certain things themselves, not least of which to protect their own position. The other book we issued before that was the Implementing IEC 62443, the Pragmatic Approach to Cybersecurity. So those were two new editions. And before that, there was the Safety Instrumented System Design book by Ewan van Beurden and Dr. Bill Goebel. We also provide a lot of free information through the website. So you can always visit exida.com and look under resources. There are white papers there, there are case studies there. These webinars are all recorded and they are available through the website too. So you could see that through the resources tab. And I always encourage people to make use of the website. We have the SAEL there, of course, which is the Safe Automation Equipment List, where if you're looking for certified devices, you can go to that and you can search under the device type. You can see the manufacturer. You can look at the certificate, and if we're allowed to publish it, you'll see the assessment report that says how the failure rates were derived. The other series of books you see down at the bottom here, the SCRH, that's the Safe Equipment Reliability Handbook. That has all the failure rates for typical devices that you would use in process applications, safety applications. And this is what's built into the Excellencia tool. So the Excellencia tool is a suite. You can either buy the whole lot together as either Enterprise or Ultimate, and you can buy the individual tools for the PHA, for example. The FACS tool is also a standalone PHA tool. We can import from other PHA tools like PHA Works and PHA Pro. And then once the data's in one of the tools, it's available to all the other tools. The LOPA tool is also a standalone tool as well. And you can pull data from the FACS tool into the LOPA tool, and then from there into the Select tool to do the SIL selection. And you can do it quantitatively or qualitatively. Then you can generate the initial SRS, the process SRS. The SIL tool is where we can do the modeling for the design of the SIF and do the SIL verification. And we can also create the detailed design SRS as well. Part of that is to create the proof test procedures. So if you have the proof test generator module, we can create the proof test based upon the equipment that's used in the SIF automatically. The SIL alarm tool is the master alarm database. So if during PHA and LOPA we identify alarms as layers of protection, then they can be pulled out and put into the SIL alarm tool to start creating the master alarm database. The SIL stat tool will enable us to gather the field data. And again, you can import from the Silver tool all the information about the SIS, SIFs, the individual equipment within each of the SIFs, and this can be geographic. So you could have it on a per plant basis in one country or across the world. So you could drill down and see the data from each of the SIFs for each of the pieces of equipment and the tags themselves. So all of that information can be stored, plus the proof test information is in there. There's a dashboard that tells you when proof tests are due, and you can then use a tablet, go out into the field, run the proof test, record all the information, the as found, the results of the proof test, and the as left, and that's automatically posted back up to a central server. So that's the suite. So let's now talk about the main topic for today, which is the sharing components between the SIS and the BPCS, and why this is not a good idea and how common cause comes into play. 1511 can be a little confusing at times, but it is very clear about the need to separate safety and non-safety. It doesn't necessarily preclude using shared devices, but as you can see in this example with our LV1, the LV1, if that's also going to be driven by the SIS and the BPCS, if it is not a certified device, then its reliability may not be as good as required for a certified device. And the other thing is, if the LV1 was to fail, it would certainly reduce the reliability of the SIS, because that particular SIF is not going to be effective, and it may also place a demand on the SIS itself for the SDV2 that would need to be closed. So we have to be very careful when we do this, and it does require a form of common cause analysis, because what we have to make sure of, and this is why it doesn't say you can't do it, but what it says is that you have to make sure that we have sufficiently low probability of failure that could be due to a common cause. And usually common cause is measured by the beta factor, which we'll talk about, but it's not just a question in this case of what the common cause factor is, it's also the failure of the shared device. And more importantly, it's the dangerous failure of the shared device. So how does it impact? Well, we should not be sharing where a failure of that device could result in both a demand on the SIF and a dangerous failure of the SIF. So again, the standard is clear about how we qualify independent layers of protection, and it's that key word, independent. And those of you that have been on my class know when I talk about SIDA or SED, the requirements for an IPL to qualify. So it has to be specifically designed to be able to prevent the hazard from creating the consequence. It must be completely independent of all other protection layers. It must be dependable in terms of having sufficient ability to provide the random failure protection as well as the systematic failure protection. And it must be auditable, which means it's got to be tested, it must be testable, and also maintainable. So of course, if we're sharing, then we don't meet the independent. Plus, the dependable is another issue, because we will be reducing the overall reliability of the safety instrumented system. So again, we should only share if analysis can confirm that that overall risk is acceptable. Because of this sharing that introduces potentially higher risk, and it is going to be dependent upon the dangerous failure rate of that shared device, because that's the thing, it's the failure on demand. Those are the dangerous failures. And of course, common cause can result in shared devices failing. So typically what we see is that sensors and valves are examples where the sharing of equipment with the BPCS is often considered. And this is mostly in legacy systems where we've seen this, of course. So it is something that has to be thought about carefully. And one of the other things that we find with legacy systems, of course, is that the useful life has often been exceeded. And that's a whole nother can of worms when you exceed the useful life. Now I see that there are questions coming in. I'm going to deal with all the questions at the end, so please feel free to register a question. So why do we have to consider common cause? Because it has an impact on the dependability, the PFDavg or the PFH from the random hardware failure point of view. So for example, here we're looking at a 2 out of 2 redundant system where we would expect a very low spurious trip, but in fact we're getting a much higher spurious trip. And so of course the question would be, well, why is that? And the answer, of course, is that common stresses can fail both units in a redundant system. So the stresses that can affect them, of course, are combinations of temperature, humidity, corrosion, shock, vibration, electrical surge, RFI, and many more. The other thing to consider is the application software would be another area where common cause, if there was a bug in the software, if there was a mistake made, a systematic problem, that could also cause both to fail. And as an example, we got asked to do just a rudimentary communication robustness test for a client. They had commissioned a subsea wellhead control system, and they wanted to make sure, since it was going to be connected to topsides through the umbilical, and communication was very, very important, of course, so they wanted a rudimentary communication robustness test done on this system, and it was a hot standby system. So our engineer went down and set everything up and started the test, and within 2 or 3 minutes, the first controller locked up. It basically stopped working. And then, of course, the secondary, the standby controller, took over. And within a couple of minutes, it too did the same thing. So now you had a completely dead system, no communication, no control, no nothing. And what it turned out to be was there was a bug in the firmware for the Ethernet driver on the control modules. So the drivers had a bug in them, and because it was the same software, both had the same bug and both caused the same problem. So that is an example of where common cause can come in through the software side of it. Cybersecurity, if you think about cybersecurity, a cyber incident can be the mother of all common cause, because if the malware gets into the system and there isn't proper protection, then it can propagate very quickly. It could go from the control system to the safety instrument system if they're connected through a process control network and there's inadequate protection. So these are all correlative events, because they can have more or less the same impact on, certainly on devices if they're the same manufacturer's devices, but also to a lesser degree, you would have that with shared devices as well. And of course, the beta factor is what I say beta, you say beta, but the beta factor is the ratio of the common cause element of the failure rate over the total failure rate. And then you can see we can split the failure rate into an independent portion and a common cause portion. So we talk about lambda CC, which is the common cause failure rate that is driven by the beta factor. So where do we get beta from in the first place? Well, 1508 provides guidance on this. It says for programmable electronic equipment, you can go from 0.5% to 5%. And for field equipment, you can go from 1% to 10%. So a conservative approach is to default to 10% for most equipment. Now you can obviously put in defenses against common cause, such as separating, if it's redundant, you can separate the redundant devices into different cabinets, different areas, run the cabling through different trunking. There was one incident where the cabling for the redundant system was run through the same conduit, and somebody was driving a forklift truck with their fork too high, and they actually took out the conduit but took out the redundant system as well. So you can do things like segregation, diversity, separation. So that's fine. And in Excellencia, we actually default to 10%. You can, as you see there, you can go through the different drop downs, and if you check all the boxes, you can actually probably get that down to about 2%. But it's important to make sure that you need to look at the balancing of the cost of maintenance. So if you're going to have diversity, you're going to not use the same manufacturer's devices, then you need to obviously have different spares holdings, and you need to, it's going to add cost to the maintenance. So you need to offset and look at the additional cost versus the benefit of having a lower beta factor. So just by way of example, we're going to go through some simple examples here. So we'll choose 5%, and we'll look at a fault tree with no common cause. And then, as you see here, we have two devices, and in this case, the system will fail dangerously if both devices fail. And then we'll look at it with a fault tree with common cause. So here you can see now that the dangerous failure can be the result of the two devices failing, or because of the common cause, which causes both of them to fail. So the whole thing fails as a result of the common cause. And let's just consider a dangerous failure rate of 0.05 failures per year. time interval of 1 year and a beta of 5%. And in this case, our lambda DCC is going to be lambda D times beta, and the normal or the independent failure rate would be 1 minus beta times lambda D. Now let's just for the time being assume perfect proof test. So what do I mean by perfect proof test? I'm talking about we can find and fix all the dangerous failures. So it's 100%, just to give you the comparison. So in the first case, what we do is we go through taking the probability of failing dangerously for the A and the B, perform the AND function, and then take the average. And I'm not going to go into the formula, but this is the formula, lambda D squared T squared over 3. And if we plug those numbers in, what we end up is a PFDavg of 8.3 times 10 to the minus 4. And we end up with a risk reduction factor of 1200. And in low demand, that would be a SIL 3. Over here now, we change our formula because we have to add in the PFDavg as a result of the common cause. And you can see the formula changes. If we plug in our numbers, you'll see that instead of it being a SIL 3 at 1200, we're now down to a SIL 2 at 500. So this simply going from not including common cause, and it's only 5%, remember, to including common cause, we go down from a SIL 3 to a mid SIL 2. And this is with perfect proof testing. So now let's consider the real world. Considering realistic proof testing. And what I'm doing here is I'm using the simplified formulas just as a means of comparison. These formulas are far too simple for us because there's several other different variables that they're not considering. But anyway, so now we have to account for the fact that when we do a proof test, we're going to be able to detect a certain number of dangerous failures, but there will be a certain number that we can't detect, which means every time we do a proof test, we're never getting back to the same place. So if we assume, let's say 90%, meaning we can find 90% of the potential dangerous failures that the automatic diagnostics can't find, then we would not be coming back down to here every time. And you can see the next time we do it, we'd be down here somewhere. So the mission time now becomes a key factor. And there, I have done previous webinars and I did an Exida Explains on the relationship between the proof test coverage, the proof test interval, and the mission time. So in simplistic terms, if we use our PFDavg as lambda d ti over 2, now we have to account for the fact that we don't have perfect proof testing. So we now have a coverage factor which tells us how many of these dangerous failures can we find, and it's usually 0 to 100%. Perfect proof testing is 100%. So we would have our CPT now times lambda d. These are the dangerous failures we can find, plus now we have to account for the failures we can't, the dangerous failures we can't find over the mission time. So if we use our 5% now with imperfect proof testing, and let's look at this example, we now have to account for the fact that we don't have perfect proof testing, and we have to account for the fact that we still have the separation of the independent failures and the common cause contribution. So if we look at it this way, our PFDavg is going to be made up of our proof test and mission time portions, each of which is going to have a normal and independent failure and a common cause contribution. So if we look at the proof test first, our lambda PT now is going to be the total failure rates, the 0.05, but now times the coverage, which is 0.9. And therefore, we end up with 0.045. So our common cause portion is going to be lambda PT times beta, which is 0.045 times the 5%. And then the normal or the independent, of course, would be the 1 minus. So therefore, we plug those numbers in, and we end up with 0.0018 as our contribution from the proof test. So now let's look at the not covered by the proof test. In other words, what's left over the mission time. So we're taking the same approach, that our mission time now is going to be our total times the 1 minus CPT, which gives us 0.005. And then we work out the common cause contribution and the independent contribution as before. And if we plug those numbers in, we end up with 0.002. If we add those two together, we end up with 0.0038, which of course is a SIL2 with a 263 risk reduction factor. So you can see what's happening is as we start to account for these things, it has an impact on the PFD average. And of course, it's an impact in the wrong direction. So we are reducing every time we account for this, we end up reducing because it has an impact on the reliability. So if we compare the results then, in the first example, we had no common cause, we assumed perfect proof test, we ended up with 1200. In the second example, we included common cause, we still assumed perfect proof testing, and we ended up with a mid-range SIL2. In the third example, we now took into consideration a realistic proof test and the common cause, and we ended up with a SIL2 at 263. So you can see, this would result in unrealistic and dangerously optimistic results. And unfortunately, there are still people that believe that doing a full stroke on a valve is 100% proof test coverage, which it's not. And there's another webinar on that one. So we have to be careful, and this is with 5% as the beta and a 90% proof test coverage. So if you have lower proof test coverage and higher beta, then obviously the result's going to be lower still. So if our target was to hit a SIL2 with a risk reduction factor of greater than 300, in the first two cases, we'd say, yeah, we've done that. But in reality, we haven't met it. And that's the other thing to remember. Well, what about some other considerations then? So when we're sharing devices with the SIS and the BPCS, the SIS equipment in the SIFs have to meet the required SIL. So this comes back to we've got to meet the three barriers, which is the PFD average or the PFH, depending on if it's low demand or high demand. We have to meet the architectural constraints and we have to meet the systematic. The BPCS equipment is not required to meet that. So therefore, the reliability may be less. And if the shared device doesn't meet 1508 requirements, then the SIF won't meet the systematic requirement. And in this example here, if that FPV 110 is not certified, then the SIS that's driving, or the SIF that's driving that, is not going to meet the required overall risk reduction in terms of, sorry, a PFD average in terms of the systematic requirement. So what we would have to do is we'd have to do a prior use justification on that FPV 110. And this would require significant data, not just the volume of operating experience, but also the quality of the data to make sure that it was accurate and we could rely on it. Common cause analysis would also need to be carried out per clause 11.2.10. So in this case, if this FPV was the source of the common cause failure, it would actually place a demand on the SIF, at the same time reducing the overall reliability, as I was saying. So we can't ignore that. So if we consider the fault tree, if you wanted to look at it this way, we would have the SIS failure and the BPCS failure, or we would have the common cause aspect, or we would have the FPV fail. And if we plug in the numbers for the FPV failure, and 8.3 times 10 to the minus 3 per year is a realistic number, the BPCS would be a 0.1, and let's say the SIS is a 0.02 per year, using a 10% beta and the same as before, we'd end up with a SIL2 with a 118 RRF. So we we've dropped even further because now we have to consider the dangerous failure of that FPV. So this is why, if you're going to share devices, you've got to be very careful and make sure that you do the analysis to make sure that the common cause aspects and the dangerous failure of the device itself is not going to give us a problem in terms of meeting target. The other thing to remember is that if we share, then we need to be having probably a prior use justification because of the systematic. You can't ignore the systematic. If you ignore the systematic, you've got to have a good reason why. So the other thing is, the standard talks under clause 11.2.3 that where the SIS is to implement the SIF of different SIL, then the shared or common hardware, including the application, because I mentioned this before, shall conform to the highest SIL. So again, we have to make sure, wherever possible, we separate the SIS from the BPCS. Because if the BPCS won't be qualified to IEC 61511, then the SIS shall be designed to be separate and independent from the BPCS. That's governed under clause 11.2.4. So in a way, the standard almost contradicts itself because it says that there's nothing stopping you sharing devices as long as you do the analysis. But here it's saying very clearly, if you're not going to qualify the BPCS to 1511, then you need to make sure they're separate. So the best approach is to, certainly for new applications, is not to do that, is to separate the SIS and the BPCS. Have the shutdown valve in series with the control valve. Have the control valve driven by the BPCS and the shutdown valve driven by the SIS. So these are the things that have to be considered. And as I said, the problem with legacy systems is that these are already there. So we just have to make sure that, number one, we are following useful life, because that's usually what happens, is these things have been running for years and they're well beyond their useful life. That's a whole different can of worms, and there will be another webinar on that. And the other thing is, if it's not certified, then we've got to do some form of systematic justification. And that, according to 1511, is going to be doing a prior use justification. All right, so to summarize then, even though 1511 doesn't preclude the use of common devices, we have to pay particular attention to the requirements in clause 11, specifically 11.2.3 and 11.2.4, which highlights these key issues and requirements. If we share devices, then we have to do some form of common cause analysis and make sure that the dangerous failures are going to be sufficiently low enough not to cause us a problem. So here again, when you share sensors, for example, sensors normally are not the major contributor to the overall PFD average. It's normally the final elements that have the highest PFD average contribution. So sensors, and this happens a lot, they use splitters and things like that to share sensors. You would still have to do some form of analysis. And again, remember that if it's not a certified device, it's going to have an issue from a systematic point of view. Now, we've helped numbers of clients do prior use justification. And it really comes down to the quality of the data and the quantity of the data that they have, especially for the final elements. And with final elements, you have to make sure that there haven't been any failures, or dangerous failures that have caused a problem. General rule of thumb, safety and non-safety should be separated where possible, because otherwise you have to treat it as safety. And what I usually tell the classes is, if you've got some control functions that are not safety related, then if they don't need to be in the SIS, get them out of the SIS. If you use non-certified devices, then you're not going to meet the systematic requirement for SIL verification. SIS designers have to justify the selected equipment for use in SIFs per 1511. And it only gives you two methods. It says you can either use 1508 certified devices for the appropriate SIL, or you have to do prior use justification. Those are the only two options that you have. So ignoring common cause for shared or redundant equipment will end up in optimistic results for your PFDavg and your PFH. So you're just fooling yourself, especially if you're assuming perfect proof testing. That's another one. And you saw the impact that that can have along with ignoring common cause. So we need to understand the effects of common cause. That's very important. You can put in defense against common cause, as I've said. You can include physical separation of redundant units, for example, in separate cabinets. You can use diversity, you can use different devices. All of that has to be weighed up against the additional costs, certainly with diversity for the maintenance. And remember that cybersecurity vulnerabilities are another source of common cause. That's why 1511 was updated in 2016 to include clause 8.2.4, which requires us to do a risk assessment, a cyber risk assessment for our SIS. And if it's connected to the BPCS and the network, then we have to include them as well. So this is something else that has to be looked at. Okay, so that is the end of the webinar, and I can see that there are questions, so we'll get to those questions. I figured there'd be quite a lot of questions on this. If you want to know more, feel free to contact us, reach out, and of course you can email me as well with any questions that you think about after the webinar. Okay, let's see what we've got here in terms of the questions. All right. Is it allowed to use the SIS system for BPCS if that BPCS do not possible to cause any failure that will activate SIF? Well, you're talking about here using the SIS to do non-safety, to do control. Yes, you can do that. Of course you can do that. It just means that you're still treating it as safety. If you have a SIS, then you should be following 1511. That's basically the bottom line. If the BPCS screen is used to show the SIS element status, how is it considered while SIF verification being a shared? Well, again, you see, that's the other thing. If you're sharing the screen, as long as there's no possibility that that can cause a demand, then if the operator is expected to do something and the operator is a layer of protection, then again, we would have to consider that when we're doing the analysis. Why sharing SIS and BPCS introduces additional risk? There is no risk if we do not take credit for control as IPL and LOPA, right? Well, again, if you're going to share the SIS with the BPCS, it will reduce the reliability, because unless the BPCS is using safety rated equipment, which it normally doesn't, then your BPCS is normally given 1 credit, at least a risk reduction factor of 10. But it will have an impact on the SIF for that SIS if you're going to share it. So in LOPA, it's not independent, and it would have to be looked at as a shared, and therefore we would have to do the common cause analysis and all the other things that I just showed you. The word independent signifies right for entire loop from sensor, cable, JB, not. Well, independent, as I said, it's a requirement. Sensor cable termination, the same trip, separate IO card on separate rail, separate power, separate control, independent software logic, or is there something could be share here? In nowadays, there is trend of universal IOs, charms, etc. which should also. Well, again, you should have separate IOs, that's for sure. And you can, the thing about the logic solvers, the certified logic solvers, the application logic that's used, those blocks are using independent memory. They're not sharing the memory. They have their own area of memory, and that's also part of the segregation, if you like. IO charms, etc. Yes, they would provide that for you. They provide that separation. You just got to remember that when we talk about SIFs, we talk about tip to tail and everything in between. So it's not just the sensor, because people say to me all the time, well, if I got a SIL2 sensor, a SIL2 logic solver, and a SIL2 final element, I must have a SIL2 SIF. Not necessarily, no. Because if you're using splitters, if you're using barriers, if you're using interposing relays, we have to consider those. We have to consider the power supplies. We have to consider the ancillaries, especially if we've got energized to trip. Communications. We have to look at the final element side, because there'll be the valve, there'll be some form of actuator, there may be a smart positioner. So all of these things have to be looked at. And that's why they need to be certified. If they're not certified, then you won't meet the systematic. If HMI goes blind, which is common for BPCS and SIS, what's recommended as per standard? Well, again, standard, as far as I can recall, doesn't talk necessarily about the HMI, because the HMI should just be a reporting for the SIS, unless you're going to be relying on the operator. And if you're relying on the operator, because the SIS is supposed to be an automatic protection layer, so in theory, the SIS should be able to operate on its own if the HMI is not there. So as long as the HMI doesn't interfere with the normal SIS operation, then that should not be a problem. This is coming back to what I said about when we do LOPAs, when we do layer protection analysis, we have to qualify each of the independent protection layers to make sure they meet the SIDA requirement. If they don't meet the SIDA requirement, then they're not going to be regarded as independent protection layer, and therefore we have to view them as either a shared layer, and therefore we have to do the common cause analysis. Nowadays, ICSS shares common network. Is it acceptable? Well, again, that's why we have the requirement now to do a cyber risk assessment. So we would have to make sure that we look at the zones, look at the conduits. If we implement the model from the 62443, we have basically we'll have a DMZ, we might have a control zone, and we may have a safety zone, and the safety zone may be separated from or segregated from the network via a firewall, and there will be firewall rules for that. If we're only if the SIS is only reporting information to either the historian or the BPCS, then we could use a data diode, because we only need information to flow in one direction. So there's things that we can do. I see some of you are having some problems with connections. Can you give an example where the failure was? Well, I just did with the fact that valve, if that's shared. My question is about cybersecurity. You talked about at the beginning. Speaking of cybersecurity, companies typically address requirements for mitigated related events from external attacks can break into the control system and compromise functional security. I would like to know if there are specific requirements related to internal hackers that invade the system through smart. Well, again, this is all covered under the 62443, and that's the reason why when you do a cyber security risk assessment, you start with a high-level risk assessment to look at where are your critical components or critical systems, and what would happen, what are the worst case consequences if they were compromised, and then you go through and do a more detailed level risk assessment, including a vulnerability assessment. So this is all defined in the 62443 as to how we do that. And you're right that typically, most of the time, it's what we call the stumbling, fumbling, and bumbling. People not knowing or inadvertently introducing problems in the system because the cyber hygiene, as we call it, is not good enough. It's not necessarily somebody attacking from the outside. And of the incidents, 80% are typically internal, and of those, 20% are intentional. The rest of the time, it's mostly unintentional. So you can do some training, you can do some other things to create the awareness. What else we got here? There's another question here which is somewhat lengthy. Let me see. That was the cybersecurity one. Overfilling protection SIF on detection of high-level close-the-filling valve, all operating connected to the SIS. How does it affect SIF reliability if SIS closes this valve as well? If there is no offloading in place and the status signal comes from the BPCS, non-safety operation reasons, there is no credit taken for BPCS protection layer, credit taken only for the SIS and the SIF defined above. Does one need to consider beta? When it comes to the common cause, if it's a single element SIF, you don't consider common cause. It's only if it's redundant. So either it's redundant, which was the example I showed you earlier, or if it's shared, we would need to look at the common cause. And obviously, not just the beta with the shared, it's the failure rate, the dangerous failure rate of the shared device. But if you've just got a SIF that's a simplex SIF, then obviously common cause isn't considered. It only applies to redundant. In the equation for CC, same for all, no redundant equipment. How about 2 out of 3? Well, 2 out of 3 becomes more complicated, but again, it's still the same approach. And what I was trying to show you was using simplified equations. The 2 out of 3 equation is much more complicated. Again, typically you won't use simplified equations. You'll be using a Markov model to look at the safe and dangerous failures and using a tool such as Excellencia. So I've just used these simplified equations for comparisons to give you a feel for what the impacts are. Can you tell me the name of the webinar for proof test of final elements? Not off the top of my head. If you go to the exida.com website, under the resources tab, look under recorded webinars, look under functional safety or certification, and you should see it there. Well, I mentioned the fact about sensors used with the BPCS and the SIF. If you're sharing them, there will be some contribution. Again, you'd have to do the analysis, but I wouldn't expect that to be the major dominating factor on the PFD average, because typically that's the final element. Is it common to have 2 out of 3 transmitters being connected to SIS and the MO03 to the BPCS? Why not? And again, it depends upon the configuration and approach. 2 out of 3 transmitters to the SIS. I'm not sure what's the MO03, M out of 3. That's what I think you're saying. To the BPCS, why not? I'm not sure I understand what you're asking me there. So perhaps you can drop me an email and explain a little further. Any thoughts about sharing with other systems such as fire and gas system? Well, again, usually with fire and gas, in the old days, we used to hardwire the fire and gas to the ESD, and that would go in through separate IOs, of course. These days, if you're using the control network to transfer information, then of course the control network would need to be redundant, and we would have to have the appropriate protection for cybersecurity. How would common cause apply to a tank shutoff valve for overfill protection prevention that is only open or closed by batch control? What do you need to consider if you want to use the valve in both of you? Well, again, if you're going to be using it in with both, then of course you've got to do that common cause analysis. You've got to, as I've shown you. Prior use by end user, or is it supplier? Well, the supplier can do it if they have the data, and that's usually the proven in use that's done from the supplier's point of view. The prior use tends to be from the end user because it's more application specific, and it should be relevant to the application that they're looking at. The requirements for prior use are that it has to be the same model, serial number, well, in terms of if it's intelligent, the same firmware. It mustn't have had any changes in order to qualify. But it can be the same device that's used in safety applications and non-safety applications to provide the hours that you need, as long as there haven't been dangerous failures. Should we expect in the future Excellencia to perform calculations for SIS and BPCS? Well, you can do it now in Excellencia. You can model it. It's just a question of how you want to model it. And again, if you want to know that, I would suggest taking the Excellencia class. How do certified devices reduce common cause versus no certified? Well, again, they don't reduce, it's not the common cause itself, it's the reliability. And because certified devices will have a certain level of reliability to meet the particular SIL. And of course, the higher the SIL, the more reliable the device, especially in terms of its inherent fail-safe features. So the common cause is with the shared devices. And if you think of it this way, a chain is only as strong as its weakest link. So if you're putting in a certified device for the SIS and you've got a non-certified for the BPCS and you're sharing them, then of course you're going to be limited by that non-certified device. And that's going to have the major impact. Can you explain what perfect proof testing is and how many people errantly assume they are accomplishing this? Well, yeah, perfect proof testing is 100% coverage. And believe it or not, we had this with one extremely well-known oil company, and I'm not going to mention them, but they had something like 300 and some odd SIFs that were all assumed 100% proof testing, which is just fooling yourself. And people believe that because they think that doing a full stroke on a valve is 100% proof testing, which it's not. And again, if you want to know more about that, there are webinars or our training courses, we go through that. I know they should not be assuming 100%, but unfortunately they do. And we've had certain discussions with that. We actually told them that we weren't going to model it with 100%. We were going to use realistic proof testing, and lo and behold, of course, a lot of their SIL 3s and their high SIL 2s were no longer SIL 3s and high SIL 2s. Final element control valve is shared between BPCS and SIS. This is the practice I have seen across major clients like Shell, Exxon, or Aramco. Do we need to consider shared devices during LOPA stage? Yes, of course you do. Because the LOPA, it should be looking at the independence. And if it's not independent, then it has to be viewed as a shared layer. And if it's a shared layer, then you have to do the common cause analysis to see what that's going to do, because it's going to have a lower amount of risk reduction. So like I said, the standard doesn't tell you can't do it. All it says is that you have to be very careful. And under a clause 11.2, if you look at 11.2, it has the caveats of what you need to do in order to be able to justify doing it. If anyone wants answers to questions via email, please email me and then I can go from there. Can alarms in BPCS and alarms in SIS shall be separate for avoiding common cause? Is there a separate standard for alarm management? Yes, 18.2, the ISA 18.2 talks about alarm management, and we can help with that. We've done that many times. But the point is, again, if you're trying to claim, as we find in LOPAs very often, people are trying to claim credit for alarm and credit for the BPCS. Now, if the BPCS is generating the alarm, then it's not independent. So it's not 2 credits. You would have to do a combined BPCS and alarm protection layer. So again, that would have to be looked at, and you can do that using fault tree analysis or using the tool. Can 2 SIFs share the same final element? Yes, well, they can drive the same final element, yes. What is the best optimal mission time? Well, again, mission time is really an end user practice, and it depends on your proof test interval and your proof test coverage and the target SIL. If you want to know more about that, there's a webinar I've done before, which I'm going to do again, to go through the correlation between mission time. But typically, we've seen 30 years, we've seen 20 years, we've seen 15 years and 10 years. Sometimes end users will look at when their valves have to be refurbished at the end of their useful life. And so that might be 10 years. So they might use 10 years as the mission time. It's really down to the end user practices. Should common cable routing, power supplies, etc. be accounted for, and how should this be quantified? Well, you can look at that in terms of the reduction in the beta factor. And as I said, if you use Excellencia, you can see how to reduce the beta. What is your view of using 3 sensors with 2 out of 3 voting in the SIS and using the median value of the same 3 sensors for control? Well, again, you can do that. I mean, that's often done, but it's a question of if you're doing it in software, where are you doing it? Are you doing it in the SIS, and the SIS is sending a signal or sending the information to the BPCS via the communications link? That would obviously need to be looked at. Could you show how you add the BPCS appointment to achieve? Again, that if you want to know more about how to do these calculations and things like that, by all means, look out for our upcoming courses, because we go through a lot of this in the course. I have a loop with a 2 out of 3 on a reactor to control temperature that is used as a SIS and BPS controlled process. If the LOPA has been considered 1 TT as BPS 1 out 2, is it correct approach? Well, again, we'd need to see the PNID, see how this is being connected and used. When we look at LOPA, you have to consider the independence. Otherwise, if it's not independent, then we have to consider it as combined. And this is where I said we have to meet that SIDA requirement. When we do the proof test, my understanding is we have to proof test individual components of the SIF, right? Well, you can do it one of 2 ways. Sometimes you can do it on a SIF by SIF basis, but if the SIFs are using the same logic solver, you don't necessarily want to keep testing the logic solver every time. So some clients do it by equipment type. So they might do the sensors of a particular type, they might do the final elements. The point is that you need to decide how you want to do that. Can SIS LT used for high-level protection be used for BPCS level control? Yeah, you can do. And again, it's whether you want to do control, non-safety control in the SIS. If you do, you just have to treat it all as safety. Is it possible to include shutdown of a motor starter as if there are not many starters that have the systematic capability? Well, usually the motor controller has to be considered as part of the SIF, so then you'd have to do a prior use. There are some now that are certified. Again, go to our SAEL on the website and have a look. Using a status signal output from the BPCS used by bypass or a startup override a SIF, does prior use need to be performed on the BPCS controller? Oh dear. Well, if you're using, again, normally the BPCS, to cover this, it's normally a 0.1 credit that's taken. So you can do a separate analysis if you think that you can do better than 0.1, but normally 0.1 would cover it. Okay, well, unfortunately, we're at the end of the time. What I'll do is these other questions that are coming in, I will answer through email. Great questions, these, and typical questions that we come across. So I will answer all your emails. and your questions. So please keep them coming. So right now, I thank you for participating. I hope you found it useful. Please look out for other webinars that we've got coming up, and also the next in the series of the exida Explains videos that I'll be doing. And keep a lookout for our training courses. Of course, if you need any help with any of this, feel free to reach out, and we're happy to help you. This is what we do. Thank you very much, everyone. Enjoy the rest of your day, and I will hopefully see you on another webinar soon.